Mindsetters, welcome to today's Grade 11 Physical Sciences show. Today we have a special revision lesson on electrostatics and electromagnetism. We have selected highlights from lessons shown earlier in the term to help you revise this term's work. So please post your comments and your questions on our Facebook page or on Twitter at LearnExtra so we can help you with your revision. You can also download the show notes for today's lesson from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
Let's quickly go through this summary here. What is a charge? Or let's look at what this thing called a charge is all about. In electrostatics, of course, we're talking about stationary charges. We're talking about those charges that are not moving. So we're not talking about electric current. We're talking about those that are stationary. Okay? And these charges, of course, are found on the surfaces of insulators. The charge is symbolized by a letter Q, and it is measured in coulombs. And of course, after the scientist Coulomb, who came up with the Coulomb's law. And the SI unit for this, of course, it is the C, the Coulomb. All right. Now, moving on. The Coulomb is a very, very big unit. So we usually use very small units. We therefore use units that are smaller to handle, easy to work with. Units like microcoulombs, nanocoulombs, microcoulombs, and what we call picocoulombs. Now, what is necessary here is that you need to be able to convert from the unit in which the charge is going to be expressed to you to the required SI unit. Remember, when we do your calculations, we expect you to use the SI unit. Okay. Now, you need to be able to convert from nanocoulomb, from millicoulomb, from microcoulombs, from picocoulombs to coulombs. All right. An object becomes charged when it gains or loses electrons. Okay, so what actually happens here is that it's only electrons that move around. Remember that objects are made of atoms. Atoms have got nucleus where the positive charges are found called protons, and the neutrons that are neutral. These ones are not moving. But around it, in energy shells, we've got what we call electrons. So when these electrons are gained by another object, that object becomes negatively charged. When these electrons are lost by an object, that object becomes positively charged. So the charging of objects are actually as a result of the transfer of electrons, either gained or lost by object. If an object loses electrons, we know, or I've just mentioned now, it will become positively charged, because at that point it has got excess positive charges compared to negative charges. If it gains electrons, of course it will have an excess of negatively charged particles. It will therefore become negatively charged. Okay, now the charge on an electron is 1.6 by 10 to the power minus 19 coulombs. Okay, right, now moving on with the summary, coming to the law of conservation of charge. We know that charge can neither be created nor lost. Okay, so it is there. This whole universe has got a particular number, a strict, okay, a particular number that is not, it can never be more, it can never be less. So if objects get charged, it's actually the charge that is there. It's either the gain of electrons or loss of electrons that are there. You can never create charge, you can never lose it. The total amount of charge in a closed system remains constant. Now, our closed system here is the whole universe. Okay, it remains constant. There are an equal number of positive and negative charges present in the universe. Okay, when charged objects touch, okay, when they touch each other, charge will be distributed, and this is very important, evenly and equally on the surface of both objects. Okay, and this equation here helps us to know how to find the new charge on objects when they come to touch each other. If I've got two objects, they come to touch each other, the new charge will be found by adding the charge on 1 and the charge on 2 and dividing by 2. What does it mean? Would I always have two objects coming to touch each other? I can have more than one, but if you have more than one, what does it mean? Say I've got 3. It means you would say Q1 plus Q2 plus Q3, and you'll be dividing here by 3. Okay, so that's what it means. So understand this formula here, which is very, very important. And of course, it is applied when we consider the fact that charge is conserved. Charge can neither be created nor destroyed. It can only be transferred from one object to another. We're looking at question number 1 now, trying to improve our skills on how to answer questions, exam questions, of course. It says here 2 isolated charged spheres, A and B, are suspended from thin strings and brought closer or close to each other. The charges experience a force of attraction. So if it's an attraction, so it means one charge is positive, the other one is negative. They touch each other and then move apart. The original charge on A was plus 5 microcoulombs. And the charge after touching is minus 5 microcoulombs. The first question says, calculate the original charge on B, on sphere B. All right, now let's have a look at it. We know that Q nu, we have got 2 spheres, so we would say Q nu would be equal to Q on the first one plus Q on the second one, and because they are 2, we divide by 2. All right. Now, the new charge, and of course here I don't have to convert here because I'm just interested in the new charge, but I can convert later on to work out other things. But then let me just work it out because we will be expected to convert, so let's use the opportunity to learn to do that. Now, if the new charge, okay, the original charge on A was 5, and the charge after touching is minus 5 microcoulombs, it means the new charge is minus 5 multiplied by 10 to the power minus 6. That's the new charge. So let me change here and call them QA and QB because the question is very specific. It refers to them as charge on A and charge on B. Now, other information that I have from the question is that the original charge on A was plus 5 microcoulombs. Okay? So 5 microcoulombs, it's 5 by 10 to the power minus 6. Then multiplied by the charge on B. That is what we are looking for, divided by 2. Okay? Now, if I am to work this out, this is going to be obviously minus 2 by 10 to the power minus 6 equals positive 5. Let me put the positive 5 there, by 10 to the power minus 6 plus, that cannot be a multiplication sign, plus QB. All right. Therefore, my QB would be equal to, okay, so this 2 times that should be minus 10. 2 times minus 5 is minus 10 by 10 to the power minus 6. Now, if I'm looking for QB, I need to take this one to the other side. And what is it going to be? It's going to become minus 5 by 10 to the power minus 6. Minus 10 to the power minus 6 minus 5 by 10 to the power minus 6 will give me minus 15 by 10 to the power minus 6 coulombs. So that was the original charge on B. Okay, sphere B was minus 15 by 10 to the power minus 6 coulombs. Okay. Now let's look at the second one, and of course it's a build up from the first one. It says how many electrons were transferred when the spheres charged indicate the direction of transfer as well. Okay. Now look, you had QA coming into contact with QB. Now we've just calculated that QB had a charge of minus 15 by 10 to the power minus 6. Now, when an object gets charged, the reason objects get charged is because objects would transfer electrons between each other or amongst each other. Now, only those that have got excess electrons will be able to transfer. QB here has got a negative charge. Definitely it's the one with excess electrons, and therefore electrons will actually be transferred from B to A. So that will be your electron transfer. It will be from B to A, electron transfer. Okay, now calculating how many electrons have been transferred, we will need to check if this was the original charge on B, and finally the charge on each of the two spheres is minus 5 by 10 to the power minus 6. How much has been transferred from there? In fact, look at that. Okay. This, after B it comes to contact with C, I mean with A, what we see happening is that we have about minus 10 by 10, I mean minus 10 by 10 to the power 6 coulombs of charge there. Now, how many electrons are there? Let's look at the difference here. The difference between the original charge and this charge here, it's going to be minus 10 by 10 to the power minus 6 coulombs. And if we want to know the number of electrons will be equal to the charge that has been, amount of charge that has been transferred. Okay, amount of charge that has been transferred. And the amount of charge that has been transferred, we found it to be 10. So we'll say that we will divide this by the charge on an electron. Charge on an electron, it's minus 1.6 by 10 to the power minus 19. Okay? And that should give us the number of electrons. Now, number of electrons, how do we get that? For that situation there, you definitely need your calculator to get that. Okay? So you will say that the number of electrons that have been transferred, okay, it will be minus 10. Okay, because it's minus and minus, just allow me to just say 10. 10 to the by 10 to the power minus 6 divided by 1.6 by 10 to the power minus 19. Okay, hope I got everything okay there. Then you get the answer there. So how many electrons have been transferred? It's 6.25 by 10 to the power 13. 6.25 by 10 to the power 13 electrons. That's the number of electrons that were transferred. Okay, good.
Okay guys, I hope you're enjoying this revision session. If you are struggling and need help, please post on the page or send your questions to the Learn Extra Help Desk. The links are on our Facebook page. But now it's time to take a very quick break. Don't go away, we'll be right back. Welcome back, Mindsetters. Even though we are selecting highlights from previous shows, you can still follow me on Twitter @LearnExtra, or you can post or comment on our Facebook page. Now, let's do some more revision.
Moving on, question 2. Okay. Consider the diagram below, not drawn to scale. All right. And 2.1 says Draw a free body diagram for all the electrostatic forces that act on Q1. Now, there is our Q1. Electrostatic forces only that are acting on Q1, not any other force. And therefore, we are going to show only two forces here, because the electrostatic forces on Q1, it's a force due to Q3, and it's also a force due to Q2. And that would mean I would have my dot to represent the what? The sphere. Remember how to do force diagrams, free body diagrams. You use a dot to represent that object. And then we know there's a force of attraction here between Q1 and Q3. So this will be the force due on Q1 due to Q3, okay? And of course, if you look, that is -6, this is -5. So this one should perhaps, in fact, should be longer in length compared to the other one, because it has got a bigger charge there. So this is a force on Q1 due to Q2. Okay, you do that, you have answered that question there. The next one is, okay, so that is where perhaps we could have done that. Let me just do that quickly. That's F due to Q3, and that is F due to Q2. These are forces, all forces on one. Let me be consistent here. All forces on one. I can put it like that. Nothing wrong about it. Okay, moving to the next question on this one. It says, calculate the magnitude of the electrostatic force between Q1 and Q2. Now, electrostatic force F is found by K times Q1 times Q2, okay, divided by the square of the distance between them. So that will be equal to, K is 9 by 10 to the power 9. It's a constant, times, you look at what is Q1. Q1, it's 4 microcoulombs. So I need to convert that. So it will be positive 4 by 10 to the power minus 6. Times Q2. Q2 is here. It's minus 6 microcoulombs. So that will be times minus 6 by 10 to the power minus 6, converting into coulombs. And then dividing by r squared, okay? R squared. Now, what is this? Here, let me put it down here. There was something missed on this question. That's 15 meters, and let me also put this one here. This one is 100 millimeters, okay? Right now, and due to this length here, let me see if that is 15 centimeters. Definitely this should be, let me make it 100 meters. Okay. Now, so what is our R there? It's 15 centimeters. We don't work in centimeters. And this, let me just go back here. That should be 100 centimeters. So at least we have got units that are relevant here. 15 meters there, 100 centimeters there. Let's come down here. It's 15 centimeters. I can't work in centimeters. I have to work in meters, so I convert that. You divide that by 100. So this will be 0.15 squared. And that is equal to, at this point, you bring your calculator, because you have to find a solution to that problem there. Okay? So let me see if I can put it that side, and we have everything to view here. So you've got 9 by 10 to the power 9 times 4 by 10 to the power minus 6 times minus 6 by 10 to the power minus 6. All right? You close those brackets and you divide that by what? 0.15. 0.15, but that must be squared. Okay, and what do we get? So what we get there, it's a force that is minus 9.6. So minus 9.6 newtons. And what does this mean? It means you've got 9.6 newtons and the force is attraction. It means you've got a positive and a negative charge that are closer to each other there. Next, let's look at the next question here. It says, calculate the net electrostatic force. Now, this is a good one on Q1. How do we do that? Now that we have got a force due to Q2 on 1, let's see what the force due to Q3 on 1 is going to be. All right, let me work it out here. That will be equal to K, Q1, and Q3 this time divided by the R squared. And that will be equal to K, we know is 9 by 10 to the 9, times Q1 is positive 4 by 10 to the power minus 6, and Q3 is minus 5 by 10 to the power minus 6. You divide all that by what? By 100 centimeters, you convert that into meters. You divide by 100 there, it's going to be 1 meter. 1 meter must be squared, okay? And you work that out. Let's use our calculator quickly, all right? You just straight away use that. So this is 9 by 10 to the 9 times 4 by 10 to the minus 6 times, what is this one here? Minus 5. So minus 5 by 10 to the minus 6, okay? We're dividing by 1, okay? Anyway, it's just formalities. We know that 1 would remain, won't change anything there. So what do we have there? We have got minus 0.18, okay? So this is minus 0.18 newtons, which is 0.18 newtons attractive, okay? Okay, now if you come back here, because they need the net force here, if you come back here, this is 0.18 newtons, and the other one is what we found out up there, which is 9.6, all right? So you can say that this is 9.6 newtons. Resultant here, or the net force here, you need to say, okay, they are at right angles to each other, so you can use this. You can say F net squared on Q1 will be equal to F by Q2 squared plus F by Q3 squared, right? Using Pythagoras here. So that will be equal to 9.6 squared plus 0.18 squared. And what is that? Use our calculator quickly. All right. We have 9.6 squared plus 0.18 squared. What do we get? And that must be squared because F net must be equal to the square root of that. Okay, so we square it, of course. That's 92.19. 92.19. That should be equal to. Okay, back to our calculator. We are to get the square. So we're getting the square on the answer. And what will that be? That will be 9.6 newtons. Okay, so that gives us 9.6 newtons. Now remember, it is a vector quantity. We need to get direction. So we need to find the angle that it makes with the horizontal. It will be tan theta because this will be opposite and that will be adjacent. Okay, so tan theta will be equal to opposite. It's the what? Is the 0, opposite is the 9.6 divided by opposite is 0.18. I mean, adjacent is equal to 0.18. We work that out, we get the tan theta, all right? That is 9.6 divided by 0.18. And what's that? It's 0.533. Therefore, theta is equal to the tan inverse of that. I think everyone can get that. And you would say that angle, actually it will be this force here at an angle of theta there. We are there with the answer. Let me give it back to Luni.
Okay guys, I hope you are enjoying this revision session. If you are struggling and need help, please post on the page or send your questions to the Learn Extra Help Desk. The links are on our Facebook page. But now it's time to take a very quick break. Don't go away, we'll be right back. Welcome back from the break, guys. Doing revision is really important, so I hope you are enjoying this lesson. I'd love to chat to you on our Facebook page or on Twitter, so please let us know how you are doing. Enough of the chat, now it's time to get back to some more revision.
Let's look at the first one, question number 1. All right, it says complete the following sketch. Okay, we've got more than one, basically, sketch diagrams by clearly indicating the direction of the current and the direction of the associated magnetic field. Okay, so we start with the first diagram here. The first diagram on 1.1, it's a conductor connected to a battery. So it's connected to a source of energy, and that battery is made up of 2 cells. We know that once we have got 2 or more cells, we have a battery. Now the trick here, we have to show the direction of current, and we have to show the associated magnetic field. Okay, so those are the 2 things that we need to deal with here. Now how do we show that? In the first place, we need to know that when it comes to current, we talk of conventional current. Okay, conventional current. Now, what does this mean? It means we're seeing current as something that actually moves from positive to negative. All right. So when we look at this battery here, there I have my positive, here I have my negative, and therefore my current I think you remember that current is denoted by the letter, capital letter I. My current I will therefore be moving in this direction. Okay, so it will be in that direction there. It will also go, it will be in that direction there. So we see it coming into the conductor in that direction. So we see current moving in the conductor in that direction. Let me put that arrow there for the current inside the conductor, because this is the conductor where we need to show the direction of current plus the kind of the associated magnetic field that will be there. What do we know about magnetic fields and current carrying conductors? If a conductor is carrying current, that conductor will generate a magnetic field around itself because there is current. If there was no current, current switched off, no magnetic field around that current carrying conductor. But once it begins to carry current, then we have a magnetic field around it. Here we know that it is carrying current, so there should be a magnetic field created around it. I'm erasing here so that I will have space to show what I'm talking about here. So we know that current is moving in that way, so we know from which point is entering our conductor. When we are to find the direction of the magnetic field around a current carrying conductor, we are to use the right-hand rule. The right-hand rule says my thumb must point in the direction of the current, and my curled fingers will then be pointing in the direction of the magnetic field. So in this case here, I do want you to see my hand, okay? Do want you to see my hand. This thumb is pointing in the direction of current, okay? I don't want that to be there. This thumb is pointing in the direction of current, and my curled fingers will go over the current carrying conductor. So it will be curled in that way. So I would have my magnetic field, if you like, on this plane will be entering into that plane of the board and coming out from the bottom of the conductor. So let me just say the going in will be represented by a dot, and the coming out will be represented by a cross. Okay, I would have this happening. Okay, and this would be representing the magnetic field, or that must be a cross. This will be representing the magnetic field around that current carrying conductor. And I can do that because magnetic, we use actually lines to represent a magnetic field. So I can actually use or show it like that, only knowing that it's entering there and coming out from the bottom there. So I have shown both the direction of the current and the magnetic field associated with this current carrying conductor. All right, now let's move on to number 2, 1.2. All right, in 1.2 we have got a coil. What do we mean by a coil? With a coil, you've got a conductor that has been made into a loop. Okay, so you've got so many windings around of one conductor, or what we call turns. Okay, then you've got your coil. So you've got number of turns of the same conductor here. That makes or gives you a coil. A coil of wire connected to a battery of 2 cells. Okay, again there is a battery. That is your positive end. That's your negative end of the battery. Okay, now, when you look at this, you would see that current will be moving in that direction. Okay? It moves in that direction. When it moves in that direction, it means down here, it will come like that. And then from the back, it will be going up, but here it will be coming down like that. Okay? That's the direction that the current is going to take. Okay? Now, if we have a coil like that, okay, of a conductor, what happens is that when we put a compass on that, we begin to see that the compass detect that the coil or that conductor that has been wound into one set of windings, turns there, creates ends that end up being a north pole and a south pole. Okay, and how do we determine that? We again make use of the right-hand rule, but this time, remember, the right-hand rule, we use it for coils or solenoids. We use it in this way. Instead of the thumb pointing in the direction of the current, we make use of the fingers pointing in the direction of the current. And when we do that, the direction that the thumb is going to take will be the side where we're going to have our north pole. In other words, that is where our magnetic field is going to radiate from and come from and get to the other side. Now let's just have a look at this. Again, I want you to have a look at my fingers here. If you look at the direction of current on the drawing that I've given you, you can actually do it this way. Your fingers in the direction of current, and you can see the direction of current there, so it's this way. Your fingers in the direction of current, all right? Then the direction of the outstretched thumb gives you your north, all right? So in this case, it will mean that we have our north end this side, okay? I will have my north end this side. Let me use a different color for this so that we all see this and understand it. So the north end is that side. Obviously, if the north side end is that side, this will be the south end. So this will behave exactly like a bar magnet. Okay, and from grade 10, we have learned that if you've got a bar magnet, you know, there is a particular way of showing your magnetic field due to a bar magnet. All right, we know that we would have things like this. The magnetic field, okay, we'll have things like that. And of course, the direction is from north to south. Okay, so you're going to have this, north to south. You can have more of this, okay, north to south. You can have more of this, okay, north to south. I'm taking care in drawing it because, you see, we need to understand how to interpret these field lines. Where the field lines are closer to each other, like at that point and that point, we talk of a strong field there. So my drawing must actually talk to those kind of things. As you move further, you will see that they become more and more far apart from each other. So away from the magnet, the magnetic field becomes less strong or weaker. Okay, okay, weaker there and stronger field there. Okay, and you can draw more of that, of course, and showing the magnetic field around that solenoid. 1.3. The view of the solenoid when looking from position X. Now, if you look from position X, this is the position X we're talking about. When you look from position X, what you would see is there is the end of the solenoid, okay? Okay, I think I should, let me just have a bigger diagram here so that I can be able to show you what I'm talking about here. So there is the end of the solenoid. So the conductor is like that, okay, on the solenoid. But what we know is that the current, okay, if you come back here, the current was going in that way. So it means in here goes the current. So it means the current there is in that direction and the current here is in that direction. So if that is the case, it means that as the conductor is in that way, you would have if you just use the right-hand rule for current carrying conductor here, you would see that if this points, the thumb points in the direction of the current, then the curved fingers will be like that. So it gets in there and it comes out from the bottom. So what you would have is things like this at the bottom part of your current carrying conductor. And the axis will mean the magnetic field is piercing through the plane, and the dot means the magnetic field is coming out of that plane. In the same way here, you would see the inside, okay, you would have it coming out from the inside. Sorry about that. You'll have it coming out from the inside. Okay, so you would have it that way, coming in from the inside. If you have your right hand rule, still going to pierce through the top here, top of the conductor, and at the bottom side of the conductor, you will have it coming out like that. So you'll have something like that if you were to view it from the side X. Okay. Right, now, question number 2. The diagram below illustrates a bar magnet moving towards a coil connected to a galvanometer that measures potential difference. Okay, so there is the galvanometer that is measuring the potential difference. Let's look at the first question. Describe what you would observe on the galvanometer if the magnet moves quickly into the coil. Okay, so you're moving it quickly, so the speed relative to the speed of motion, the relative motion there, it's quite fast, and it then stops. What are you going to see? Now, this is the bar magnet. It goes in there in some very fast speed. By doing so, it induces an EMF. Induces EMF into the coil. Okay. But then if you check here, there is the negative end and that is the positive end. when you push this magnet into the coil will work out in such a way that it makes this side to be the north pole, because there it's your north pole of the bar magnet. It always opposes what is happening there. And if that is the north pole, okay, so the induced EMF will be such that the current will start by going in that direction, because it has to come out through this other end to give you your positive conventional current moving of the positive charge. Okay, so when it goes to the negative end, what does it mean? It means that your reading on the galvanometer, okay, your reading on the galvanometer will start by going in the negative sense. Remember, the 0 point is there. Okay, so the going to the negative end means that your negative end is that. It will first go that way. And when this thing stops, because we're told it stops, then it will come back to what? To point at 0. Remember that without that relative motion, there is no EMF that can be induced onto your coil or your conductor. All right. So that's what we are going to see happening there. 2.2, use the diagram to illustrate what happens when the magnet is pulled out of the coil quickly. Now, this time, the coil is, the magnet is now pulled out of the coil quickly. So it goes out this time. What will happen? When it goes out, okay, the current will go in the positive this time. It will be induced into the positive. So it will first go to the maximum positive. It decreases until it also comes back to what? To the 0 mark, after it has completely gone out and perhaps come to a stop, like we are told there. All right. In the first part, it had to come to a stop. But when it is moved out quickly and it is out and comes to a stop again, that's what we're going to see. The galvanometer will come back to its 0 mark. Okay. Question number 3. Okay. A solenoid with 450 turns has a cross-sectional area of 176 square centimeters. Now, we don't work in centimeters squared. We need to be working in meters squared. So immediately there, you could see we've got a problem, and therefore we will need to sort it out. There should be some conversion there into meter squared. Meter squares, not centimeter squares. All right, it is positioned perpendicularly to a uniform magnetic field of 0.72 Tesla. All right, the first question, 3.1 says, all right, calculate the flux, the magnetic flux through the solenoid. Okay. Now, magnetic flux, that it's given by the strength of the magnetic field times the area, okay, and times the perpendicular component of your your magnetic strength there. All right. Now, we are told that the magnetic flux is in such a way that it is positioned perpendicularly, okay? Or in fact, this cross-sectional area is positioned perpendicularly to this uniform magnetic field. Okay, so what we have is that already the plane is there, there is the area, and it is perpendicular to it. We don't have it at some angle to the normal. And what is the normal we're talking about? There is the normal, the line perpendicular to the plane. So it's not at an angle, it is exactly at 90 degrees. So what does this mean? It means that the two, the normal and that one, are along the same, they are parallel to each other in the same direction, and therefore the angle between them is 0 degrees. So this will therefore be cos 0. Now let's calculate for phi, the magnetic flux. Right, the magnetic field strength is 0.72 times. The area is given to us as 1.76 square centimeters. It must be in square meters. So it means we're going to divide that by, you divide by 10,000. And when you do that, it gives you 0,0176 square meters. Okay? And when you work that out, let's see what we have here. When you work that out, okay, and of course this side, we need to take care of the direction there. Of course, like I said to you, the angle is 0 degrees, and I've shown you why it is 0 degrees. So we can work it out here, right? We say this is going to be 0,72 times 0,0176 times the cos of 0. And the cos of 0, of course, is what? It's a 1. So that should actually be giving us just 1. So this works out to be 0,0127. So this is equal to 0,0127. 7 watt. This is measured in Webers. Okay. That's the answer there for your first question. The next one, 3.2, it says, calculate the induced EMF if the solenoid is pulled out of the magnetic field in 0,22 seconds. Now, EMF equals minus number of turns change in the magnetic flux divided by change in time. Now, I think you remember what I said about the negative, that it is all about the direction that the solenoid is going to have in terms of the north, each north. If you bring in a north, it will bring a north onto it. So it always acts against whatever external influence or effect that is brought about by the movement of that magnet, bar magnet in this case. So we are told that this number of turns, it's 450 turns. So this will be minus 450 turns times, what is our flux from our calculation here? It's 0,0127. So 0,0127, it's our flux. So change in flux, when it goes in and comes out, it means it is from 0. It is actually from a value to some 0, okay, to a final value of 0 Weber. So you would say that this is 0 minus 0,0127. So 0,0127, 0,0127. And that should be divided by the time. Change in time, it's 0,22 seconds. And what do we get at the end? What do we get at the end? We make use of our calculator quickly. We've got 450 minus 450 times, this is going to be a minus, so immediately, okay, that is going to be a minus there, you can see. So immediately, I just leave out the minus before the 450. So 450 times 0,0127, 0,0127, and you divide that by the time, 0,22. And what do we get? Let's have a look at it. It works out to be 25,97,98 volts. 25,98 volts. So that is 25,98 volts. Okay, that is the EMF that will be given off, or that will be induced onto that particular solenoid.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Please visit our website, learn.mindset.co.za, to get the notes and to watch the videos from earlier in the year. And remember, we are here to get you through the year, so stay connected. Goodbye.